So normally I was on schedule to give this lecture, but because of the cancellation that we had, I'm jumping in and giving a lecture on a topic of geoprotective drugs. So I don't have to show this, you all know. Aging is the cause of most of the chronic diseases, so you know that as well. So the outline of the talk is I'm going to talk about the types of geoprotectors, their effects, and then I'm going to say, there are quite a lot of geoprotectors in the literature. If you want to do really big, well-done studies, so studies in hundreds of mice, you want to select out which drugs you will test, and you can all pick your own favorite drug, but that's obviously not a very good criteria to judge upon. So is there a better way? And our previous speaker actually showed one method to select drugs, and I will show another one, namely the hallmarks of aging, which we saw yesterday, and I will show some results. So geoprotectors, you all know, are treatments that reduce the rate of aging and thus increase the lifespan of the organism. So the types that have been described so far, there are inorganic ions, and I only know one of them, lithium. I don't think any other inorganic ion has been shown to extend lifespan. Small molecules, there are many of those, including, for example, metformin, on which we had a lecture. There are peptides, proteins, such as fibroblast growth factor 21. And there is extracts of natural sources which contain small molecules, inorganic ions, a whole mixture of them, as they often are not purified up, such as experiments using green tea extracts. So you can also classify them differently. Now this is from the literature, I don't agree with everything on this slide. And the examples on the right three are only examples, and many of them will fit into different categories. So you have antioxidants, anti-glycation agents, anti-inflammatory drugs, anti-amyloidosis drugs, inhibitors of growth signaling, sirtuin activators, calorie restriction mimetics, and this is of course not an exhaustive list at all. And as you can see, for example, metformin has well-known inhibition of NF-kappa B, and so it's an anti-inflammatory drug, so it fits in this category as well. It's also said it will be anti-glycation, so it fits in this category as well. So this is just some examples that I give that are prototypical, but they fit in multiple categories. So the problem is, in the literature, nobody really knows, there is not a complete database of geoprotective drugs of all lifespan tests ever done available, although there are several incomplete databases. I know one person who says he has an exhaustive database but doesn't want to share it, he wants to commercialize it. So, but we guess that there are about 1,000 or even more compounds that have been tested in C. elegans, Drosophila, mice, rats, some organism yeast, and have been shown to extend lifespan one way or another. So that's only compounds, not genetic interventions, of course. There is no consistent method to classify them, and there is no methods, as I said earlier, to select the most promising ones. You can take your pet drug, but that isn't a good way of working. So lifespan studies are expensive and time-consuming, especially if you go to very high organisms like primates, for which only calorie restriction has been tested. So the NIA, Interventions Testing Program, which is the best rodent study in the world, we can see that without doubt. They do it in 3 different universities at once, and then compare in hundreds of mice over all sites, and for each site, and overall they measure the lifespan effect, and they see if there are inconsistencies. So that's like triple replication. So the ways you can classify geoprotective drugs, or you can look at lifespan data. That's very important. So if you want to select a drug to test in a very large study, you will look at what studies have been done before, and you will select, of course, only drugs that have been before shown to extend lifespan. If you want to do a large study, if you want to do a C. elegans study, of course you can take whatever compound, because you can test thousands of them. But you will, for large studies, only look at, and that's what ITP does. They ask, you can send in your proposal to them, and you need to prove that the drug has before shown to extend lifespan. You need to show that the drug is possible to give without toxic effects, and so on. So we actually, me and several others, have submitted such a proposal, and you need to prove that. And our proposal was not accepted actually, because they found that the evidence was not strong enough to warrant, because the ITP can only do 5 interventions about a year. Maximum they have ever done is 6. And that includes also different concentrations of the same drug. So generally they only use 1 concentration, but sometimes they do 2 concentrations when, like with rapamycin, in the second time they did it, they tested several concentrations. So you can also look at microarray data, and that's what Steven Spindler is doing. He's looking for calorie restriction mimetics, and he looks at what does my drug do on the microarray profile, and if my drug replicates the microarray profile of calorie restriction, then I'm going to test it for lifespan. The problem with that, of course, is that you only find calorie restriction mimetics, and not all life extension drugs must mimic calorie restriction. So another way is to look at mechanical evidence. So what is the evidence on signaling pathways that my drug will extend lifespan? And we can say this is where our previous speaker showed one example of. So maximum versus mean lifespan extension, I think I'm preaching to an audience of aging researchers mostly, so you know it. It's important to look at maximum lifespan or the mortality rate doubling time when you want to claim that your drug really influences the aging process itself. Obviously, drugs that increase mean lifespan are also very interesting, but that may be due just to the prevention of one disease and not necessarily by delaying aging itself. So calorie restriction has been shown to extend lifespan. There are 2 primate studies going on. They have a bit of inconsistent results, but certainly in lower organisms, calorie restriction is without doubt the most well-tested, well-studied intervention. You have rapamycin, which was already mentioned earlier. So these are the original data from the ITP, which gave 14 and 9% increase in maximum lifespan, but follow-up studies using better concentrations, because this was just a random concentration they took, have increased to almost 30%. So then metformin, which has been discussed earlier as well. So here is in the C57 mice, there was an increase of 5.8%. And so it has failed in yeast as well. This is the human data that we collected and that we are going to publish, but we haven't done that yet. So basically here is 0. Everything below here is a reduction in mortality. This is in type 2 diabetes patients. And everything above here is an increase in mortality. And there is actually only one strange study. The size of the bubbles, by the way, is the size of the study, the number of subjects included. So one small study of 254 patients where there was an increase in mortality for an unknown reason. Aspirin has also been studied. So you have an increase in lifespan, mean lifespan by 8%, and the pooled 19% mortality was increased. However, maximum lifespan was not reported in this study, and it also failed in female mice. So the had 3 mice, those are the mice specifically designed by the ITP to be long-lived and healthy mice. So resveratrol, which was published a lot about and has made a lot of headlines in popular media, when in 2006 it was found to increase lifespan in mice fed a high-calorie diet. However, since the ITP has tested it and it completely failed, it also has failed in yeast, well, in some studies and not in others, so there is ambiguity there, but it failed in normal weight mice in the ITP, which is a very good study. So I don't think resveratrol is very interesting, to be honest. So based on lifespan data, I will say, if I have to classify it, this is of course my opinion, at least in all lower organisms, so below primates, we can certainly see that calorie restriction is still the golden standard. Rapamycin is certainly second place. Metformin, which is being tested by the ITP, but the results aren't published yet, but does have quite a few data behind it. Aspirin, and then resveratrol on the last place of this list. So the hallmarks of aging, DNA damage, epigenetic changes, which we heard a lot about today, telomere shortening, which we discussed a bit yesterday, cell senescence, which we discussed yesterday, mitochondrial dysfunction, this is proteostasis, so that we discussed also yesterday, stem cell depletion we have here some about, deregulated nutrient sensing here, and intracellular communication. So what we have done is we have used those 9 hallmarks and made a hallmarks of aging score. So we basically are going to see for each of the drugs how do they influence each of these different hallmarks of aging. And we have the number of positive influence hallmarks and we divide it by the negative influence hallmarks. In this person, that's just a correction factor to avoid some of the problems that you will have without it. And so scoring systems are in common use in the clinical field at least. So a HAS score between 0.1 and 10. 0.1 is the lowest evidence, 10 is the highest evidence. So the way you use this is you have 1,000 drugs or so that have been previously reported to extend lifespan in one organism or another, and you want to make a list to test in really big studies. So my method is only for really big studies, right? It's only for, if I want to spend a lot of money, I want to do a study on something that is really promising. So what do I take? And that's why you are going to use the HAS score and, of course, looking at lifespan data to make a list of which targets to go off, and you can test them. So let's look at calorie restriction. And very interesting, if you look at rodents, calorie restriction has been mentioned in the research to be positive for all 9 hallmarks of aging. So for each of these hallmarks, we have generated a list of things we check out. So we, for example, if you look at genome stability, we check out nucleotide excision repair, base excision repair, translational synthesis, oxidative DNA damage, the amount of ROS in the cell, so the potential for DNA damage, and so on. So for each of these categories, we have a whole list of things that we check. And then based on that list on how these drugs influence all of them, we judge if the effect is positive, negative, or unknown or neutral. And so that's when it's unknown, the effect. Here, this you can see in primates, there were studies that showed that these 2 hallmarks, the genome stability and the telomere length, was in contrast to rodents not improved. So basically you can see that the HAS score must be lower for primates than for rodents, and it is. And so actually you can see that just missing out on these hallmarks reduces the HAS score. So a very high HAS score means that it's almost completely positive. So preliminary data, we have here calorie restriction, that's only for lower organisms. Rapamycin, for all the drugs, of course, only lower organisms because they are never tested on primates. So that's positive on genome stability, proteostasis, mitochondrial dysfunction, nutrient signaling, and intracellular communication. Metformin mimics rapamycin, except that it has a negative effect on cell senescence, and there was actually one very good paper that tested it in a whole range of different, including in stem cells, and really showed with different markers of cellular senescence, as we had a discussion yesterday, that beta-Hal staining doesn't indicate that the cell is senescent. You need to look at multiple markers of cell senescence, and there was a very good paper that actually showed that metformin is negative here. However, this might be responsible for the anti-cancer effect of metformin, so that's something to keep in mind. Aspirin is also beneficial for genome stability, mitochondrial dysfunction, cellular senescence, stem cell exhaustion, and intracellular communication. However, there are some data that it's negative for nutrient signaling. And finally, resveratrol, which scored really bad in lifespan tests, also scores really bad in the HAS scoring, because it's really, there are several studies, and we only look at studies in, so not in cell lines, but in primary cells, because obviously the cell line may be actually, that's a cancerous line, so you don't want to basically look if it's good for cancer cells. You want to look at primary cells. And in primary cells, resveratrol has been shown to have negative effects on the genome. Also negative effects on cellular senescence. So, that's a bit bad, isn't it? So the HAS score, calorie restriction 10, rapamycin 6, metformin 3, aspirin 3, and resveratrol 2.5. And actually you can see that the HAS score and lifespan data are actually pointing the same direction, that these are the most promising interventions and these are the least promising interventions. Now, of course, these are just 5 drugs that we selected. The test will now be to make a HAS score for all 1,000 drugs, and that will take quite a lot of effort. First, a database needs to be made that is exhaustive of all studies ever done, and then we will have better data. So I want to acknowledge Victor Bjork and Avi Roy. Avi Roy has really come up with the idea, so it wasn't me who invented it, but he sadly couldn't make it here, so I'm presenting the lecture. And Victor Bjork has helped with accumulating all the data for this presentation. So thank you very much, and I'm pleased to take questions.
Thank you so much, Sven. It's really amazing that we have new practical approach. My question is very easy. Why don't people list vitamin D3 as geroprotectors? We have data that it decreases mortality and hopefully extends life.
Vitamin D3, you said?
Yeah.
Yes. Well, we didn't list that because we just took 5 compounds of the 1,000 to look at. And of course we took 5 compounds for which there were enough data to make a nice presentation. I'm certain for a lot of these 1,000 other compounds that have ever been claimed to extend lifespan, the data are not really so complete. So then you will get much less good evidence. Yes.
Thank you for a very, very clear presentation. I understand the need for classification, but to be honest, I'm a little bit, well, doubtful whether this simple classification and whether one drug affects, for instance, genomic stability or epigenetics, whether this really is feasible and applicable. You know, what if you said, for instance, calorie restriction affects epigenetics in mice, how? I mean, there are so many effects on epigenetics. How can you say that there's a yes or a no? And to make it even more complicated, it affects one another, right? So if you have epigenetic changes, it affects genomic instability and vice versa too. So I think this classification, although I understand that it's difficult to be optimized, I think it needs to be very critically assessed.
Yes, I do want to point out that this is purely a method only to select interesting things to pursue further. It most definitely is not trying to come up with saying that because the HAS score is high, this drug must be geroprotective. That will be a wrong interpretation. This is only a tool that you use to take 1,000 compounds and say which one am I going to look after. And that's, if you use this tool, the one that has the highest scores. In large testing, that is. So it's really clear it's a tool only for selecting for large studies, and it's only a tool to select compounds to test. It's not a tool to prove that something has an effect. And I also have to make clear that I actually don't completely agree with the hallmarks of aging, as was pointed out yesterday by someone else, for example, is that completely extracellular aging, so cross-linking, which I do believe has a role in aging, is completely ignored here. So, I'm actually not even fully agreeing with this model, and I think we should probably go to a better, more inclusive model. But obviously we took this from last year that was published, this large Hallmarks of Aging paper, but we hope that just like with the Hallmarks of Cancer, there will be an update, or we could make an update of it, where we go more exhaustive.
Forgive me if you've already covered this, but are you going to look at specific cell types? Because you mentioned about resveratrol not having an effect, but in the brain, microglia show shortening telomeres. So it might be some of those compounds work more specifically on different cells than others. And so, are you going to differentiate between which cells are beneficial? Because in some diseases you might want to target a different cell type. It might not be applicable to all the cells.
Well, for this, you are using data that have been published in the literature. So, I mean, nobody is going to do experiments just to calculate the Haas score.
Yeah.
In most cases,
okay,
right?
So are you going to use data out there?
So you are just going to look at literature.
Yeah.
You are going to look at all the studies done. Our approach is to discredit any study that is done in a cell line that is cancerous, because obviously that will, you want to make, there is clear distinction. There are often, if you look at drug interventions, there are often opposite effects between a cell line and a primary cell. So you really want to focus on primary cells if you have to go to cell lines at all. Ideally, you look at animals themselves that have been given the drug, and then you extract tissue and look at those tissue. Yes?
What made you then come up with a new type of classification? I mean, we have sense with the 7 hallmarks of aging, if you say so. So these guys must have the feeling that their classification is better or more suited. So you know why is that? Or?
Well, I mean, yesterday we had it in the panel session with Aubrey. I asked, do you think this is inclusive? Do you think hallmarks are missing? And I also first pointed to Aubrey and said, you have made something that is quite similar to what they are proposing, right? So, I mean, yeah, I don't know the reason that they propose something different. I haven't talked to the authors and asked them, why aren't you going with Aubrey's model and are introducing a different model? But the model does fit on many occasions, like DNA damage, epigenetics, and mitochondrial dysfunction. That's all the same.
As you said, the cross-linking is the extracellular cross-linking, for example, is missing.
Yes. So they must have thought that the evidence, as we had discussion yesterday as well, that the evidence wasn't strong enough to warrant that cross-linking is involved in
no,
aging.
they just forgot it. I asked them.
They just forgot it.
Yeah.
Okay.
Sven, thank you for this very clear and very interesting speech. I have one general remark. My conviction is that no product, or at least no classical product, is ever going to make really a big difference for human beings, at least for maximal lifespan. Now I come to my question. So you certainly know about the Methuselah Mouse Prize. This is the prize with an award for people who can make mice having a longer maximal lifespan and also a longer average lifespan, I think. But why there are so many tests the last years with new products? So what's happened that nobody won this prize anymore since 2009?
Well, it's certainly true that genetic interventions still have been proven to work better than any drug that has ever been tested. The reason is unclear, I would say, but obviously the genetics are often much more severe that you are going to do. So if you do a knockout of growth hormone, you really knock it out. If you are going to inhibit it by a drug, you are only decreasing it by a certain percentage. So, the fact that you get more severe phenotypes when using genetic interventions might be the reason that you get much bigger lifespan extending effects. But drugs, I mean, we have like 30% almost with rapamycin at optimal concentration, which might be another problem that people have often just tested one or two concentrations and never tested different concentrations and might not have just found the optimal dose as well.
Just to say, I hope to be wrong, but since I've seen so many studies, and actually for maximal lifespan, it's always less, and yeah, of course for human beings we don't know because we don't have time.
Of course, it's actually even worse than what, it's actually even worse than what Didier said. It's not just that drugs don't do as well as genetic interventions, it's also that genetic interventions, with only one exception, never do any better than straightforward calorie restriction. The one exception being the tenfold thing with worms. Yeah, we haven't beaten McKay yet. Clive McKay in the 1930s managed to add 30 or 40% to mouse lifespan.
Oh, yes. Well, that's true. I can only agree.
Well, just to say one very, sorry, it's very specific, but regarding mice, we've had a wonderful description of the Ames dwarf mice, and they live about 50% longer and 70% longer than the controls. So maybe it's me who read that or don't understand the sentence to better.
Yeah, let me elaborate. So of course, it depends what strain you use. As I can't remember who was talking about it yesterday. Holly, of course, mentioned, it's not those mice are not on a C57 black 6 background, and shorter-lived mice tend to be easier to extend the lifespan of.